the TM mode is eta naught. Put that up there. Eta naught is simply, it's the characteristic of piece that guides dielectric properties. So I'm calling it eta naught the square root of mu over epsilon. And really, you can call it eta naught is equal to 120 pi times square root of mu relative over epsilon relative. In free space, it's just 125. I'm bringing your, because I sent up somebody to grab the quizzes. I had them on the outside Dropbox in my office, and we'll get going in a second. Y'all follow me on this class? So today, what I'm planning on doing, oh, you're back, D. You have 2 pairs of sunglasses? You got those? Oh, it's a mirror, though. You're going to have to take my word for it. Because we tried this thing.
I remember I'll bring 2 unmirrored ones.
If you can find some.
I think I have to.
I actually, I don't know where it is, but we have polarization actually filmed. And if I can find that, I'll bring it down myself. I just want to show you guys that because it's an interesting thing. Something that makes it real. Okay, now, the way I always start my classes, first, any questions about the homework or anything we've talked about up to this point? We basically went through the TM mode last time, right? And so now we're going to do the TE mode. Just get that down here. For the TE mode, this is the one, the 1.0 mode, 1.0 TE mode is the dominant mode that the waveguide operates in. Let me go through it. I'll start right here. So, now when you have TE, that's transverse electric mode. Yeah.
Are we talking about oblique incidence right now? Or
this is waveguides.
There's
Oblique is chapter 6. This is waveguides, chapter 7. Nothing to do at all with oblique incidence. Right. Even though you're right that we could have TE and TM at oblique incidence, but now we're just talking about waveguide and the relationship of TE and TM.
so the equations are separate?
Yeah. Did you do the homework?
Yes.
All right. Well, with waveguides, what's the real thing? They're confined to a tube, right? We don't even talk about angle of incidence or angle of transmission. There's none of that. Basically, we're talking about the modes when we're talking about waveguides. For the oblique incidence, you're talking about the angle of incidence, angle of transmission, and Brewster's angle for the TM case. By the way, these are the quizzes. I'm going to pass them around. Please just take yours and pass it on back. And the solutions are up there. So, again, chapter 7 waveguides covered the TM mode of the waveguide, right? In formless. And I gave you homework which related to TE and TM. If you did the reading, you won't have any problems. So for the TE mode, you find out that now you're basically saying transverse electric, or EZ now, is 0, and you only have an HC. Now, when you go through these equations, I want to just say one thing. Let me ask you this. How many people actually read the book in this area where we talk about TE and TM? Okay. If you read it, congratulations, you're way ahead of the game. If you looked, and how many tried the problems that I gave you? Okay, if you tried them, some of the stuff is a bit confusing because you had to go back to the chapter and see what they're referring to if you did the reading on that. Please try to keep up with this because this particular stuff can get very confusing very quick if you don't stay on top of it. There's a lot of things that you really have to nail down in your understanding. So for this one, we will have an HC, all right? Because now we're talking about transverse electric, or the electric field has no component in the direction of propagation. Before it was TM, right? We did have an electric field. Now, when you go through the equations for this, you actually are going to get, instead of having a del squared with EZ, you're going to have a del squared with HC, and it's going to be plus, and really, then this is going to be beta unguided squared times HC equals 0. Let me tell you where this is in the book. I can, you all know how you can develop that from the 2 Maxwell's equations? I'll get that in one second. I just want to show you where we are. So this is on page, if you in your book, 394. But I'll tell you where they come from. And let me do it over here. need to write this down, you know, but at least you should have an appreciation for how that equation came about. When we start with the two Maxwell's equations, we have curl of H is equal to, normally, it's sigma E plus J omega epsilon times E. I'm just gonna write it down the way it would be inside of a waveguide. This would just be J omega epsilon E. Sigma would be 0. And then you would have curl of E here is equal to minus J omega mu times H as such. Then we're gonna get one equation with only one unknown, but this time we want it in H, not E. Y'all follow me, class? So what we're gonna do is take two, we're gonna take another curl of that equation. We get curl of H here is equal to J omega mu, or sorry, J omega epsilon times curl of E. Well, there's my curl of E, so I just put it in, minus J omega epsilon, or J omega mu times H. And then we get J times J is minus 1 with a minus sign is plus 1. I get omega squared mu epsilon times H here is equal to this. This breaks down to the gradient of divergence of H minus del squared of H. That's the general form of it. Can anybody tell me something about that is very important? If you're a physicist, if you get a physics degree and you didn't know this, you probably never get your degree. There's something about that divergence of H equals 0. Does anybody know what it is? Okay. Let me just make sure that you appreciate this. What is the divergence of D? Anybody? Or divergence of E? Either one. What do we call those? That's the point form of Gauss's law, right? This is rho V, right? That's charge density. This one would just be equal to what? Rho V over epsilon, right? All right, both of which are important. If you're charge free, these are 0. Now, what is the divergence of V? Why? You're right. You're right. That's right. It would imply a magnetic charge. It's always 0. Y'all follow me on this, class? And I say this, and then somebody's going to take a high-level physics course where they talk about the CERN super colliders that they have over in here, where there's the atom smashers. And there is, at least I've read, some evidence of, quote, magnetic monopoles, singular magnetic monopoles that exist for like femtoseconds. They suppose, now I'm just going to tell you, that's the world that we don't live in. In the macroscopic world, there are no magnetic charges, no. And that means this term goes away automatically. I don't have to make any assumptions. Just remember that. Some of you are going to run into this. I do too. I run into this all the time on some of the stuff I have to deal with at when we deal with quantum physics and things like this. You get into areas and there's bizarre things happening. Anyway, so that equation becomes simply del squared of H, and then it's going to be minus, and this is, you can call this beta unguided squared times H equals 0 as such. Actually, plus that, my bad. Plus that, and this is the equation that I just wrote up here. Now, we're only going to do the HZ component. Remember, in general, when we have both the E field and H field have 3 components, and that means when you do a del squared operator, you're going to have 9 total terms if you do it right. But when we do this one, we're going to assume HZ itself, we're going to use separation of variables, can be rendered as just some function of X, just some function of Y, and just some function of Z. Y'all remember doing this? This is standard separation of variables. Then we go ahead and we plug it in here, and we're assuming this is just the HZ component. We're not messing around with the HY or HX component yet. We'll get those later. So when we go ahead and put them in there, to this equation, I get the second derivative. I'm going to write it out for second derivative of HZ with respect to X squared, plus second derivative of HZ with respect to Y squared, plus second derivative of HZ with respect to Z squared, plus, and then it's going to be beta unguided squared times HZ equals 0. So I just wrote this down one more time, and I've taken the del squared operator and I expanded in terms of its derivatives. Now when I put this in here, I got a double derivative with respect to X, so this equation is going to become x double prime y z plus, and then it's gonna be x times y double prime z plus, then it's gonna be x, y, and z double prime plus beta unguided squared times x, y, z equals 0. At that point, that's called separation of variables. We did, in fact, get separation of variables, you'll see in a second, when I divide top and bottom of this equation by x, y, and z, the functional form, x, y, and z. Y'all follow me? So if you divide by the functional form, this becomes x double prime over x as before. This becomes y double prime over y, just like before. When we're talking about the TM mode, and this becomes z double prime over z, and this just becomes beta unguided, all equals 0. Follow me? Just like when we did the TM mode for the EZ, right? Same exact thing. Now, the only way this can happen, if x is just a function of x, and y is just a function of y, then its double derivative is just a function of x. And the only way just a function of x plus just a function of y plus just a function of z can be a constant is if the functional form here, x double prime over x, is a constant. And they label this as simply minus beta x squared. This constant is simply minus beta y squared. This constant I label as minus beta z squared. In Dr. Wentworth's book, he just calls that beta. And so I'll make a note of that. This is minus beta squared, Dr. Wentworth's book. And this is just beta unguided. So now you have, as before, minus beta x squared, minus beta y squared, minus beta z squared, all will be equal to, well, all plus beta unguided squared equals 0. And that's the standard equation that you develop for both PE and PM modes. Then we solve it. And when we solve this is interesting. Now remember, this is for H, it's not for E. So when you solve this thing, we'll start right there. No, we'll start with this one. So now I have the second derivative of x, the functional form of x squared, and then it's going to be plus beta x squared times x equals 0. Now the only thing I've done here, as I said, this is equal to minus beta x squared, and then I multiply by x, and then take everything to one side. That's the only thing I'm doing. The double prime just means two derivatives, so you get this. Now this is a standard homogeneous differential equation, second order homogeneous differential equation. We could solve it using Laplace transforms, or you know that this is going to have a canonical solution. You can just put in the form of the solution, x is equal to e to the lambda x, and take a double derivative of that. And you'll find, in fact, that lambda itself is going to be plus and minus j beta x. So now your form, the functional form that you can have here, will be either a cosine of beta x times x, or a sine of beta x times x, or possibly e to the plus or minus j beta x times x. Those are the allowable forms. And the way we figure this one out, which is different from the TM case, this is 8z. Now I'm going to put my waveguide up here. And the internal of that waveguide looks like this, where I have, this is the x-axis, this is the y-axis, z is out of phase, this is the origin. The dimension of this is A, and the dimension of this is B. All right, and that's just inside the guide. We're looking right, you know what, I forgot to bring the waveguide. Now I'll bring it on Monday, I'm sorry. Tied up in a line. All right, so coming back to this thing, now, we're solving for this. Remember, this is the form that the H field takes. Now, before when we did this, we knew one thing. We knew that the tangent value of the E field was zero on those things. In other words, EZ was zero, so that solution in X had to be zero at those boundaries. Do y'all remember that? At the four boundaries. This is different. This is the H field. Now, the H field's interesting. The H field on a conductor's surface has, if you're talking about any kind of periodic behavior, it has the tangent value of the H field has a relative maximum. Y'all follow me on this? If you were to actually plot the magnitude of the H field, if this is, say, this is a perfect conductor here, and you were to plot the magnitude of an H field versus altitude here or something like this, you would find that it would come and would have a relative maximum there, and always a relative maximum, which means the derivative of the H field with respect to the normal direction, the derivative of the tangent component of the H field with respect to the normal direction will be zero. In order for this to have a relative maximum, the derivative has to be zero, right? It has to be zero with respect to the normal. So, in that case, we know the derivative of this actually has to be able to go to zero all here, 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 and here, which means it has to be the cosine. Derivative of that cosine would be a sine. Do you all see that, class? Now the sine, even though the derivative would be what? It would be derivative of cosine is going to be beta x times the sine of beta x times x. That will be zero when x is zero. And it will be zero, we can force it to be zero when x is a by selecting beta x times a and setting it equal to m pi. As a matter of fact, I'll just say this right now. The solution for both x and y will be cosine of beta x times x. And in fact, what will happen is, and will be the same for the y solution, it will be cosine of beta y times y. And beta x will have the same exact values as it did for the TE or the TM mode. Beta x here will be equal to m pi over a, and beta y will be equal to n pi over b. Now, we can do this, and what Spokey talks about, you can take a derivative of this, you're going to get beta x times the sine beta x times x, then set, it automatically checks the box when the x is zero, it's zero, and when x is equal to a, then you put beta x times a is m pi, and you get that. And same thing with y. Now this is in the book. What page is that on? Oh, well, I thought you were. I'll tell you where it is. This is on page 396. He goes to the derivation of that. And he talks a bit about it. He doesn't even explain the boundary condition, but that's the reason. And finally, in 7.74 on page 397 is the form of HY. He gives the rest of the forms too. Now he does have in my book the correct form for the TE mode impedance on page 398, equation 7.79. Do you have that? That's the correct form. Yeah, that's the correct form for the TE mode characteristic impedance, and keep that in mind. All right. So now this follows the exact same procedure as we did for the TM mode. And at the end of the day, here's what you're going to end up with. And this is important. When we go through this whole thing, we find out that now our HZ, this is for the TE mode, HZ has the form of some H naught, just a constant, cosine, and here it's going to be m pi over a times x. Then it's going to be cosine of n pi over b times y, and then it's going to be e to the minus j beta, I like to put beta z, whatever it does at times z. And this would be hz. Here, beta z is given by, we can solve it over there, but it's gonna be the same beta z that we solved for before, and this is gonna be basically beta unguided times the square root of 1 minus fc over f squared. Now, y'all remember last time when we did this, we showed what cutoff frequency was? Same thing happens here, it's the same exact thing. Beta unguided is equal to omega times square root of mu epsilon. So this is really the value of beta that has to do with the material used inside the guide itself. It has nothing to do with the dimensions of the guide. And that will be beta z. And remember one other thing, FC in general, now I'm going to make some other comments in a second. FC is a function of m and m, or the mode numbers, and that's equal to 1 over 2 square root of mu epsilon, and then it'll be equal to that times the square root of m over a squared plus n over b squared. Write that down. It becomes a little more useful, I'm about to tell you. That's the cutoff frequency, that's HZ. He shows in the book the values for E and for H, for EX, EY, EZ, and everything like that. When you actually have this form, you can go ahead and you can take a curl of this form, take the curl of H, and you can find out from there you can get every single, all the other field components. You can do it, all right? Takes a while, it's irritating, he does it. The real thing about this is, at this point, if you look here, right here, this is the important part. That's HC. Now, hear me. If you have m and n equals 0, then you have a cosine of 0 is 1, cosine of 0 is 1. So you have h naught times e to the minus j beta z times z. You'll find when m and n are 1, beta z is also going to be 0, nothing propagates. So you can't have a mode number 0, 0. But you can have a 1, 0 or a 0, 1 mode. And the lowest order cutoff, and this is important, the lowest order cutoff frequency is the F, is really going to be cutoff frequency for 1, 0. And if you look at that, that's 1 over this 2 square root of mu epsilon, and then it's going to be the square root of just 1 over a squared. There is no, I mean, m is 1, n is 0. Y'all follow me? All right, what is this really? Let's take a look at this. This is 1 over 2 square root of mu epsilon divided by a, isn't it? Correct? All right, keep looking at that for a second. That's equal to, well, what is 1 over square root of mu epsilon? If it's mu naught epsilon, that's the speed of light. Really, this looks like the speed of light if we're assuming we have a wave at its air fill divided by 2a. Now, that's the cutoff frequency for the 1O mode. I want to show you something. When you have the 1O mode, and we take a look at the H field itself in here. All right, there is no Y variation. Y'all see that? Because N is 0, so there's no Y variation. There's only a variation in X, and it's a cosine. And what it does is this. The magnet, if you actually, you can forget about Y variation. If you just thought about magnitude of HZ here, and you plotted it versus X, what you'd find here, peak there, and try to do this in a way. It would be this. If I put magnitude, it would do this. All right. That's what it would look like. And here's the real thing about this that's important. If you actually look at this, remember, this dimension is A. So at the lowest order cutoff, this dimension is half a wavelength, right there. It's exactly 180 degrees of change, but it's a half wavelength. So if you say that A is equal to lambda over 2, lambda is 2A for cutoff. Y'all follow me on that, class? Now take a look over here. Well, what is wavelength? It's C over F cutoff. So it would be C over F cutoff 1, 0. Or F cutoff itself would be equal to C over 2A. And that's exactly what we have here. The way, I remember when I was being taught this, and I did early on, a lot of stuff with, not a lot, but did plenty of research with waveguides. When you had a standard waveguide in a 1-0 mode, you know just by looking at the horizontal dimension, that told you that's half wavelength of the cutoff mode for the lowest frequency possible. So you could automatically figure out the cutoff frequency for that waveguide, and therefore the frequency of operation is a little bit, it's greater than the cutoff frequency, and typically it's, if the cutoff frequency is going to be C over 2A, the next highest frequency, the next mode will be, it'll go from 1-0 to 2-0, and that will be simply C over A, or it'll be double that. So that means between the first cutoff frequency and the second cutoff frequency, the actual waveguide will operate so that no other mode could operate. Y'all follow me? Normally, what they'll do is have, if the cutoff frequency is like 6 gigahertz, that would be for an X-band waveguide, then they'll operate it somewhere about 8 to 10 gigahertz, in that range. The next cutoff frequency will be 12 gigahertz. They'll never get near 12, and that will prevent any other mode from ever being developed. So all the electromagnetic energy or power will propagate at the same velocity. Y'all follow me on that? That's real important. That's normally the way it's done. It's almost all TM guides, or almost all waveguides that are rectangular, operate in a 1-0 mode, and they do so where their operational frequency is probably about 2/3 of the way between the first cutoff and the second cutoff mode. And I'm saying that, I'm kind of hedging like that too, because I'm thinking of some special cases, but that's about right. So, now.
Would there ever be any reason any advantage to having a waveguide that operates in a higher mode, or?
Well, there are specialty cases where then, the problem is, the minute you have a higher order mode, like if you have a 2-0 mode, now you've got energy propagating at 2 different velocities. So how do you know how much energy is at the 1-0 and how much is at the 2-0? Frankly, you don't, but what they do is this. They have something, and it will be a design filter that will bleed off the 2-0 mode, so only the 1-0 mode will propagate. But they can send 2 modes down the same guide, same piping and stuff like this. Then they bleed off the 2-0 mode if they need it for something, and the 1-0 mode will be left if they can do it. But this is a lot more trouble than it's worth, in my opinion. It's better to have 2 guides, just run them in parallel. Normally speaking, you don't ever want to do that. I mean, I don't know of a condition where they do it, but with circular guides, it's a little different, but we don't actually do we don't solve the equation for the circular guide. I mean, if we had a circular waveguide installed, you find the dominant mode will actually be a TM mode. But I'm not going to go ahead and do that, because your book doesn't do it, he doesn't touch it, he requires Bessel functions.
Are there any other common shapes of waveguides other than rectangular and circular, or really size?
That's it. I mean, theoretically, you can have an elliptical guide, you can have anything like that, but it's not going to buy you anything, as far as I know. I mean, if it does, it's something I don't know about. I will say one thing too. The rectangular guides, the metal guides that we're talking about, they are used for high power applications, and they're great. High power, I mean, you're getting up around a gigahertz, coax just won't cut them, and you basically lose too much power with coax needles. When you get up with a waveguide, you got gigahertz or more, you don't really have that much loss. You have some loss, but not an outstanding amount. It's used all the time for high power. But most of the time, for communication purposes these days, they go to fiber optics. And fiber optic guides are either slab guides if it's on chip, and that's just a rectangular guide made of just dielectric materials, or it's really an inner core, outer core fiber, and that's glass. That's the way it's done nowadays. It used to be a real pain because whenever you cut one of those things, to get it back to working, you had to fuse it, and it would. But now they've got that technology fixed. And we'll get into fiber in a second, but fiber optic are really important. Now, what I'm going to do now is I'm going to show you. I'm going to put down contrast TE to TM. Show you things that are common, things that are different. Remember, lowest order mode is always TE10. That's critical for a rectangular guide. I'm going to show you how to waveguide impedance changes and how you do a classic problem that's not in his book. So first, let me go down and put down, we started with TM, right? TM mode. Here, the general field equation is started by getting EZ equal to some E0, and it's going to be, and I'm talking about the standard waveguide, it's going to be times the sine of M pi over A x times the sine of N pi over B times Y. That look better. Then it's times e to the minus j beta z times z. That's the E field. From that, I'll do T right next to it. Here's the word common to all. First, we talk about beta z, which is Whitworth's beta. That's simply beta unguided times square root of 1 minus fc over f squared. That's the case. And of course, beta unguided is just equal to omega times square root of mu epsilon. Next thing that will be given is k itself is just the square root of 1 minus fc over f squared. Remember, fc, it depends on the mode number. There's an fc10, fc20, fc30, and stuff like this. And in the problems I gave you, they said calculate the first 9 modes, lowest order modes. So you've done that. Next, after this, now we talk about the actual waveguide's internal impedance, and you can call it unguided, but it doesn't really matter. That's the square root of mu over epsilon inside the guide, which is 120 pi times square root of mu relative over epsilon relative. When we talk about phase velocity inside the guide, it's omega over beta, and that's really going to be equal to one over the square root of mu epsilon, and this is divided by k. That's the phase velocity. Group velocity is actually 1 over the derivative of beta beta z with respect to omega, and that will become equal to 1 over square root of mu epsilon times k, and k, of course, is that. It's phase group velocity. Now over here, for the TM mode, the characteristic impedance, ZTM, that's equal to simply beta unguided times K. And over here, for ZTE, that's equal to beta unguided over K. That's shown correctly in that last one I gave you, that equation. Got group phase velocity, beta Z. All right. And I want to say one thing. This beta Z is really beta in waveguide. So, or along the guide. Maybe you can call beta along the guide. It means it's the beta that you would use in the standard waveguide, or the standard equations to govern the impedance of a waveguide. Now, the E field and H field equations, if you want those things, are in the book. I don't ask that because that's usually not asked for. If we were actually talking about power conducted down a waveguide, we'd go through the derivation of that in a more formal way. But I'm going to show you how this is really used. Now, you all can see that really that characteristic impedance and that characteristic impedance will be, well, you probably maybe can't see it, but you know how when we've done transmission line problems, the characteristic impedance of the transmission line became critical in calculating everything about standing wave ratio and everything like that. We're going to see it will be exactly the same with a waveguide, only the impedance inside the guide now will be like the characteristic impedance of the transmission line. So that's what I'm about to do, and I'm going to do it right here, I think. Yeah. So here's a classic problem. Write this down. It's not in Dr. Wentworth's book. It's a very classic problem. So I'm going to put a source here, and I'm going to have some source voltage at a given frequency. All right, just a standard oscillator there, standard feed. Then I'm going to have some source resistance. Then I'm going to attach my waveguide. It's a rectangular guide. I'm going to attach it right here. And the waveguide itself, I'm just going to show it like this. The waveguide will have dimensions, horizontal dimension A, vertical dimension B. This is going to be a metal guide. And the way you feed these things is with a little filament antenna, ground this. And you can have a cap guide here. The waveguide is going to have a length L. Please write this down. We're going to assume Z equals 0 here, which means the value here is Z is equal to minus L at the opposite end of the guide, just like with how we did this with transmission lines back in the day. Then I'm going to have a regular. I'm just going to show this as a load here, and this is going to be some. Well, I'll make it ZL instead. I'll make it some ZL. That's going to be the load impedance. Now, technically, what's usually here is a horn antenna or something like that you just cap right on there. So this is a classic problem. You got the length of the guide L, but the waveguide impedance here is going to be Z, and it depends on the mode. We're going to assume it's a TE mode, and it will be ZTE 10. That is the most common frequency of operation of the guide. Y'all follow me on this? So now, I'm going to come over here and solve this thing for you. And here's what we're after. We got a voltage here. We want to figure out, obviously, we'd like to figure out the voltage at the load, and we'd like to find out the power at the load. We want to see how much power is delivered to the load. That should stand to reason. Those are two questions that are very important. So, when we come down here, I'm assuming it's operating in the 1 ohm mode. So, first thing, we get the cutoff frequency for the 1 ohm mode with my guide. Now, really, if I give you a problem like this, I'll give you dimensions A and B. You're going to figure that out for yourself. But it would be equal to simply what? Well, it's going to, technically, it's 1 over the square root of, 1 over 2 square root of mu epsilon divided by A. That would be the 1 ohm cutoff, all right? Whatever it is, doesn't matter. whatever that frequency is, we're gonna operate the guy at, and I'll just say F is equal to 1.5 F cutoff 1 volt. So it's 1.5 times the cutoff frequency, not nearly 2, which would be the next step frequency. Y'all follow me in this class? So that's what I'm operating at. Now, what is this really gonna look like, this mess right here? It's gonna look like a transmission line problem. But here's the difference. You remember, for transmission lines, you had a characteristic impedance Z naught, right? That we used. Now your characteristic impedance Z naught will be equal to really eta U divided by K. Alright? And K, of course, is equal to square root of 1 minus FC over F squared. Now, for our case, I've told you that we're operating 1.5 FC, right? Can y'all follow me on this? Please make sure you see this little bit right here. I've just made that determination. That means my value of K right here will be equal to the square root of 1 minus FC over F is 1 over 1.5, right? Squared, right? What's that? Can anybody tell me? I'm just kidding. Well, that's, we gotta take what? You're right, it's 2/3 squared, so that's 4/9 divided by minus 1. That's 5/9 square root of that is square root of 5 over 3. What is the value? Anyway. I do this so you can look back and go through the problem and see everything.
0.745.
That's, K values of that are normal. That's about right. Okay. Have that. So my next step is, I'm gonna get this impedance, right? And we'll assume it's air-filled guy. So if it's air-filled, that's 120 pi divided by 0.745, whatever that is. I don't know. Is it a pro? Come here, computer.
It's not that.
No.
You got 161.1 pi.
Well, how about,
Sounds about right.
yeah.
Another 6.
506 ohms. Now, after that, now I'm gonna look just at the wave guide, but I'm gonna make it an analogy to a transmission line. We're gonna have a transmission line of sorts with a characteristic impedance Z naught equal to this. Alright, we've got a length L, and I've got a ZL here that I haven't defined yet, but I'm just gonna leave it as ZL for now. Now, what we have to do is get the input impedance right here. I've gotta get Z in to this wave guide. And Z in to the guide will be equal to, now remember, this is the standard transmission line equation. It's gonna be Z naught, right? Then it's gonna be times ZL, it's lossless, plus J Z naught times the tangent, but here it's tangent of beta Z times L over Z naught plus JZL times the tangent of beta Z times L. Alright, now I didn't give you a ZL. I can do that in a second if you want. But beta Z is the critical thing. This is not beta per se. It's beta Z. It's beta along the guide. And beta Z, right, is equal to beta unguided times K. Y'all follow me on that. Now, the L is gonna be whatever L is in meters, but this will give you the input impedance to that guide. You remember doing this stuff for transmission lines? All right? Now, from there, what we have to do is this. Now we come over here, and we have our ZN. So the first thing we do is we look at how much of this signal is actually going to be on the way to guide. Erase the rest of this. So I don't need this. So I have VS here. Now this is my source resistance. And now I put down my impedance. I better just do it like this. Call it ZN here. And now I want to figure out the amount of voltage plus the minus V prime that occurs there. Remember, that's going to be the voltage that literally hops on the guide. It's going to be a summation of the voltage traveling, or the voltage waveform traveling down the guide and also reflected back at that point. And that V prime is simply going to be equal to Vs, whatever Vs is, times Zn over Zn plus Rs. That should look familiar, right? You remember? Now, inside the guide, the way they actually solve it, you don't have to solve this in terms of the electric field's value. There is, in fact, for the T10 modes and stuff, there is a measurable voltage that's at from the top of the guide to the bottom. Follow me on this? If you literally put a probe in there, you could measure that. So it's much the same as a transmission line in terms of how we go about defining what happens inside. You know, for a transmission line, you didn't define the electric field everywhere versus times or versus space or time. You define the voltage, right, between the inner and outer conductor, because it's the easiest thing to measure. Same way here. Now I say this is actually just equal to some V0 prime, and it's going to be times E minus J beta Z times Z plus the reflection coefficient at the load times E to the V plus J beta Z times Z. Now that's the general form, but we're at Z equals minus L at this point. Y'all follow me? You remember this right here from transmission line theory? Same exact thing. Now here's the one difference now. Z here is going to be minus L, because that's, we're at that end, we're at the value, or the place where this thing, the signal is actually fed into this. So now this becomes a plus right there, and this becomes beta Z times L, and that becomes a minus. And this becomes E to the minus J beta Z times L. And we need V0 plus, so we see that V0 plus here is equal to V prime. I'm just going to leave it as V prime. I know it's that. It's that divided by E to the J beta Z times L plus the reflection coefficient of the load times E to the minus J beta Z times L. And that will give you V0 plus. The reflection coefficient at the load is simply equal to Z of the load minus Z naught, that would be the waveguide impedance we calculated, over ZL plus Z naught. I'm not going to have time to finish this whole thing. But that's how you get V0 plus. Do you all follow me in that one, class? Once we have the reflection coefficient that's it's determinable, now we can get V0 plus, which is the key to this whole operation. Because once we have V0 plus, please write this down. Now we can get the voltage at the load. The voltage at the load will just be equal to, remember this equation right here? Now, the value of Z is 0 at the load. That's how these things are set up. Right there, Z equals 0. So our voltage at the load is simply V0 plus times 1 plus the reflection coefficient of the load. A lot of you remember that, I'm sure. You all follow me? That's the voltage at the load. So how do I get the power at the load? Anybody? Well, here's the trick on this one. Now, if this is an inductor, no average power would be consumed. You follow me? If that load was a capacitor, no average power would be consumed. You all follow? You would have peak power, but no average power. So what you really can think of is you wanna find the resistive component of the load, and wanna take that and then multiply by the magnitude of the current squared divided by 2. You could do it that way. The way that you're shown with Dr. Gross and everybody else is the power of the load would be equal to 1/2, and then it would be the real part of V times I conjugated. That's the way you were doing it back in the day, right? Well, you can write this as simply 1/2, then you can take, you can basically do it this way. You can take VL as such, square it, and it's going to be divided by the magnitude of the impedance here, and then it's the cosine of the angle of the impedance here. Now, I want you to understand something. This is the impedance. I'm showing you the impedance of the load, pardon me. I'm showing you the magnitude of the impedance of the load. All right, let me just make a comment. If the impedance of the load is either an inductor or a capacitor, right, then that angle would be 90 degrees, and the cosine of 90 is 0. Y'all follow me? If the impedance of the load is strict real, then it would be cosine of 0 degrees, which is 0, and you would have just 1/2 VL squared over ZL, and that's the standard power dissipation for a resistor, right? Here, VL is a peak value. Y'all with me? I'm gonna give you some problems on this. That I know isn't in the book, so I'm gonna take you through it again on Monday, some stuff, but I'm gonna give you some classic problems, and please keep up with this. I'm not gonna give you a quiz on Monday, but you may be getting a quiz Wednesday and Friday, because we're back, we missed a few, okay? And if you wanna see a waveguide, come on upstairs. Are there any extra quizzes back there? All right, thank you.